All right, question 46. This time we're going to do some differential equations. Specifically, we're using the method of undetermined coefficients. A frustrating thing about this test is there's so much information that it could possibly cover. So you spend time learning or reviewing methods like this and then just kind of hope they show up on the test. The bad news is it's entirely possible that you learn this method and then it doesn't come up on your test at all. But the good news is the method is relatively straightforward, and I'd say there's a decent chance that it'll show up once. This method of undetermined coefficients solves second-order differential equations of the form y double prime plus, maybe p of t times y prime plus some other function, maybe q of t times y equals some third function, g of t. In the simplest case, and in this problem, p of t and q of t are just constants, which prevents the algebra from getting a little untenable and likely be more than what you'd see on this test. So maybe for our purposes, hopefully you'd be using this method to solve y double prime plus some constant a times y prime plus some other constant b times y equals some function g of t. Unfortunately, or maybe fortunately, this method only works for specific functions, g of t. I think the most common case is to have g of t be a polynomial. Maybe I'll say an nth degree polynomial. But it also works for exponential functions, maybe c times e to the dt power. And for linear combinations of sine and cosine. So c1 cosine of dt plus c2 sine of dt. Note that c1 or c2 could itself be equal to 0, which would allow you to solve a second order differential equation equal to, sine of pi t or something. Anyways, the way that you use this method is kind of in two steps. You find the homogeneous solution and then the particular solution, and the sum of those two give you your answer. The idea for the homogeneous solution is we set g of t equal to 0, and then substitute e to the rt power in for y. The reason you choose e to the rt power is because the derivative of e to the rt with respect to t is just re to the rt, and the second derivative would be r squared e to the rt. So when you set up your homogeneous equation, in this case y double prime plus 2y prime plus 3y equals 0, this substitution will give you a nice polynomial to solve. Let's see, y double prime would be r squared e to the rt power, 2y prime would be 2r e to the rt power, and 3y would be 3e to the rt power. You might notice that each of the three terms have an e to the rt in them. So you factor that out in front and you get r squared plus 2r plus 3 equals 0. So either this equals 0 or this equals 0, but this can never be equal to 0. So you end up with just r squared plus 2r plus 3 equals 0. This is what's called the characteristic equation. And it's worth pointing out that you can kind of go directly from here to here without actually doing this substitution. Right? Change y double prime into r squared, change y prime into r, and y just turns into a 1. Takes your homogeneous equation, turns it into the characteristic equation. We solve this equation for r, and then plug in those two roots into this substitution, and our answer is just a linear combination of those two exponentials. So generally, it's a really easy process. Unfortunately, in this specific example, the roots are going to be complex. All right, you can use the quadratic if you want, but I kind of prefer to complete the square. R squared plus 2r plus 1 is a perfect square. It's r plus 1 squared. Subtract 2 from both sides. Take the square root. You got r plus 1 is equal to plus or minus the square root of 2i. So r is negative 1 plus or minus root 2i. In case you're just learning this, maybe I'll solve a different homogeneous equation right next to this, right? If the problem were y double prime plus 2y prime, minus 8y equals 0, maybe I jump straight to my characteristic equation, r squared plus 2r minus 8 equals 0. I'd factor to solve, r plus 4, r minus 2 equals 0. So r is either negative 4 or positive 2. I take these two roots, I plug them into e to the rt power, so I get e to the negative 4t power and e to the 2t power. Then the solution to my homogeneous equation, sometimes it's y h of t, is just a linear combination of these two things. So some constant, maybe capital C1 times this thing, plus some other constant, capital C2 times this thing. Right? It's a quick and easy process. What if your roots are complex? Well, it's kind of the same idea, right? You might kind of think that I'd get a linear combination. So C1 times something plus C2 times something else. And here these somethings are e raised up to the negative 1 plus root 2i t and negative 1 minus root 2i t. And that works out fine, but things get kind of messy. First, you could distribute the t through the parentheses, and then recognize that e raised up to a sum is the same as the product of two different e's. So e to the negative t power times e to the square root of 2i t power. Same thing over here with c2. We could factor out this e to the negative t, but we're still left with these exponentials involving these complex numbers. At this point, if you're really trying to show all your work, what you would do is you'd apply Euler's formula, right? That e to the it power is equal to the cosine of t plus I sine of t. Playing the role of t here is root 2t, and over here it's negative root 2t. So that would kind of give you 4 terms, 2 with cosines, 2 with sines, and these arbitrary coefficients, which I guess I forgot to write here, out in front. But since these are arbitrary coefficients, you can combine things and just create different arbitrary coefficients. And when the dust all settles, you could end up with e to the negative t times some other arbitrary coefficient, I'll call it c1 again, just being lazy, cosine of the square root of 2t plus c2, again a different arbitrary coefficient than what I have here, sine of the square root of 2t. There are a series of logical steps that would get you down here, but I don't know anyone who solves these by actually remembering these steps. I think what most people do is just sort of memorize that this is the form that you want if your roots are complex. I guess a little bit more generally, if your roots are a plus or minus bi, the form that you want is e to the a power times c1 cosine of bt plus c2 sine of bt. This would be the general form of our homogeneous solution. So since a was negative 1 and b was the square root of 2, the general form of the homogeneous solution is what I wrote right down here in red for some reason. Like, wow, that's a long process, but at least I'm done. Well, not quite. Remember, your general solution is the sum of the homogeneous solution and the particular solution. What we just came up with is the homogeneous solution. If we got really lucky, only one of these answers would have that homogeneous solution and we'd be done. Unfortunately, we're not really lucky. It's not this thing. Although if you factored incorrectly, if you thought that the roots to the characteristic equation were negative 1 and negative 2, you'd end up with this part of the homogeneous solution. C and D are missing the e to the negative t power, so those aren't our answers. So it must either be D or E. All right, here's our homogeneous solution. So all that's left to do is take a look at the particular solution, or more specifically, figure out if the particular solution is just t, or is it 1/3 t minus 2/9. The way you figure out the particular solution depends on what your function g of t is equal to. So as we talked about before, this method works for kind of 3 different classes of g of t. If g of t is an nth degree polynomial, then what you start out with, kind of your guess for the particular solution, is just an nth degree polynomial. If g of t is an exponential function, then your guess is just an exponential function with an arbitrary coefficient. So capital C instead of little c maybe, e to the dt power. So if g of t were, I don't know, 3e to the 4t, you do ce to the 4t. And finally, if g of t is a linear combination of sines and cosines, your guess for the particular solution is just an arbitrary linear combination of those sines and cosines. So maybe a cosine of dt plus b sine of dt. D being the same number you see here, a and b being the constants that you're going to solve for. Anyways, in this case, we have an nth degree polynomial, specifically a first degree polynomial, this polynomial t. What that means is our guess for the particular solution will just be an arbitrary first degree polynomial. So I don't know, like right here maybe, y p of t for the particular solution is equal to a plus bt, right? First degree polynomial. All I got to do is solve for a and b. How am I going to do that? Well, I'm going to figure out the first and second derivatives. So the first derivative here, pretty easy to figure out. This goes away. This just turns into a b. The second derivative even easier. This is a constant, so the derivative is just 0. I'm going to take this information and I'm going to substitute it into the original differential equation. So instead of writing y double prime, I can just write 0. Instead of writing 2y prime, I can write 2b. Instead of writing 3y, I can write 3 times a plus bt. That should be equal to t. If I distribute and combine like terms, I got 3a plus 2b plus 3bt is equal to maybe 0 plus t to really illustrate the process of what's going on here. I have this constant that has to be equal to 0, and then I have this linear term, 3bt, that must be equal to t. So equating their coefficients, 3b must be equal to 1. If 3b equals 1, b is a third. If b is a third, 3a plus 2 times 1/3 must be equal to 0. So 3a must be equal to negative 2/3. So a must be equal to negative 2/9. Remember, my particular solution was of the form a plus bt. So since a is negative 2/9 and b is 1/3, my particular solution is negative 2/9 plus 1/3 t. Recall that the general solution is the sum of the homogeneous solution and the particular solution. The homogeneous solution we've already circled in blue here. I guess that's not a circle, but you get the point. I know it doesn't look like it, but this is a plus here, not a minus. I just drew over it. Here's our particular solution. Looks like the answer to this question is E.